video, let's try to see how to practically solve some problem with the help of ANN. Here we are taking this fake regression.csv, which contains three columns. First one is price, and then we are having feature one, and followed by we are having feature two. So based on this feature one and feature two, we need to predict the price. And if we carefully observe this particular price column, by seeing this itself, we can clearly say that this is a continuous variable. And if we are having continuous variable as our output, then it will come under regression problem. And we already know in case of n and what changes do we need to make if it is a regression problem. I hope you have already seen my previous NN videos. If you haven't gone through that, please go through those videos. You'll get to know what changes do we need to make. So let's jump into this particular code video. First, we are loading this particular fake regression.csv. And if you want this particular CSV file, you can simply type this name on Google. You'll be getting the Kaggle and GitHub links for this. Okay. If we read this using pandas, after loading, we can check this using df.head. And also you can check the info, which will be telling some details like we are having 1,000 number of entries and it is having floating point values in each of these columns. There are no null values in all of these features. All this information we'll get to know by seeing this particular df.info. After that, let's try to use some plotting techniques in order to understand the data. So whenever you have very less number of features, so here in this case we are having only two features, right? So like that, whenever we are having less number of features, it is better to use something called as pair plot. So what pair plot will be doing? Pair plot will take each two pair of features and try to plot graph between them. Okay, so that is what pair plot will be doing. Basically, if you are having two features, it will be giving 2 into 2, that is 4 number of graphs. If you're having three features, so basically here we are for pair plot we are sending price, feature one and feature two. So total it will be considering it as three features, and total it will be giving us 9 graphs. So let's see how these 9 graphs are looking like. So in the diagonals it is comparing like price with price only. So there is no point in comparing price and price. It will be giving us some straight line. That's why instead of showing it like a scatter plot, it will be giving us a histogram. And similarly here it will be giving histogram for feature one, and here it is giving histogram for feature two. And I hope you guys know what histogram does. Basically it will tell us at this point what is the count of like data points that we have, that it will be telling us. Basically it will be telling us the distribution of data based on the input that we have. So based on price, so this is the distribution of data that we have, and based on feature one, this is the distribution of data that we have, and this is based on feature two. And remaining are like this particular graph is showing relation between price and feature one, and this particular graph is showing relation between price and feature two, and similarly this is showing a relation between feature one and feature two. Like that, each of these graphs are representing some information, and these are just the reverse. So basically these graphs are not needed. If we have these three, just the reverse of it will be getting these three. Okay, so I hope you guys understood what pair plot is. And by seeing this, we can understand that feature 2 is somewhat more related to this price because it is exhibiting behaviors similar to some straight line. So using feature 2, we can directly predict how price is varying. That we can understand by seeing this graph. And using maybe feature 1 and feature 2, we can extract out even more information and get even better result. Okay, so let's continue how we are going forward. Let's see. So first we are keeping all our input columns in X, and then we are placing our output column, that is price, in Y. After that we are doing train test split. So we are giving testing size to be 0.3, which means that 30% of the points will be there in our testing data set, whereas remaining 70% will be there in the training data set. Total 700 points will be there in training data, and 300 points will be there in testing data. And in X test, there are two columns because we are having feature one and feature two, whereas there are no columns in case of Y train because will only having some array of outputs. Okay, so that's why it is 700 comma 300. And now let's do some pre-processing. So we have discussed various pre-processing techniques, right? So one of such pre-processing technique is normalization. In normalization, we'll try to scale down the data to 0 to 1 region. So in order to do that, we can use something like min-max scaler, and we have seen this normalization respect to video already, how to do min-max scaling and all those things. So basically we'll just initialize this, and then we'll be passing this extend to our fit method. Once we pass this, it will try to calculate the min and max values, and after calculating it on transform, it will apply that particular formula, that is x minus min by max minus min. Okay, so which will make every input to in the range of 0 to 1. So previously my inputs might be something like this, like here if you see it is 999 and 999, but after scaling it down, our inputs will scale down to 0 to 1 region. Okay, and then finally we are building our neural network. So in order to build neural network, we can use this TensorFlow. From TensorFlow we can take this sequential and dense layers. So first we'll initialize it with sequential, and then we can add as many dense layers as we wanted. So here if you observe, there are 3 dense layers that we have added initially, and each having 4 number of neurons. Okay, so each of this dense layer you can think of it as hidden layers, and finally the last dense layer you can think of it as output layer. And in the hidden layers, the activation function that we are using is ReLU, and we have already discussed what ReLU is and how it will be useful for us in the previous videos. Okay, so this is our neural network. Let's try to see diagrammatically about this particular network. Okay, so basically in the first layer we'll be having input 1 and input 2, that is x1 and x2, or this can be something like feature 1 on feature 2. Okay, the first layer will be having feature 1 and feature 2, and followed by we'll be having our first hidden layer, and we have seen that there are 4 neurons in the first hidden layer. So this is my hidden layer 1, and this is my input layer, and then followed by we are having another hidden layer which is again having 4 neurons, and then followed by another hidden layer which is having again 4 neurons, and finally we are having one output layer which will be giving us the predicted output. Okay, and basically as this is a regression problem and we are having only one output, that's why we are having one neuron in the output layer. Okay, so if you're having multiple outputs, let's say 2 outputs, then you can have 2 neurons. And what is the activation function that we'll be using? If it is a regression problem, we'll be using linear activation function in the output layer. And in remaining hidden layers, we have already seen we are using ReLU as our activation function. And now can you guys calculate what will be the total number of parameters in this particular ANN? And what are the parameters? Basically our parameters are the weights in this particular neural network. Where we'll be having the weights? We'll be having the weights on the connections. So this particular input will be connected to all these 4 neurons in the hidden layer 1, and similarly this will also get connected to all the neurons in the hidden layer 1. Like the total, how many number of connections we'll be having? We'll be having 2 into 4 number of connections, and on each of this connection we'll be having one weight, and along with this, for each of the neurons that we have, we'll be having one extra bias term. So for this we'll be having one extra bias term, for this we'll be having one extra bias term, for this we'll be having one extra bias term, and also for this we'll be having one extra bias term. So total in W0 we'll be having these many number of weights, and similarly in W1, this output that we get from this neuron will be connected to all other neurons in the hidden layer 2, and similarly over here, and similarly over here, and also over here. And what will be the number of weights in W1? It is really simple. It will be 4 into 4 plus 4, and by now we have discussed this multiple number of times. And here also it will be 4 into 4 plus 4. This is the number of weights in W2. And finally the outputs will come connected to the neuron in the output layer, and here the number of weights should be 4 into 1 plus 1, and we'll be getting our output. And once we get our output, basically what is our data set? Our data set is having feature 1 and feature 2, and also we are having price, right? So in price we'll be having the actual value, that is y1, and then input we'll be having x1, x2. Initially we'll be initializing all the weights to some random values, that is w0 weights, w1 weights, and w2 weights to some random values. And after initializing them to some random values, what we'll be doing, we'll be sending this x1 and x2 over here. So instead of f1 we'll be passing x1, and instead of f2 we'll be passing x2. And once we pass these two, we'll do some forward propagation. On doing the forward propagation, we'll reach over here, and finally we'll be getting the predicted output. Now we have our predicted output given by this ANN, and also we have our actual output in the original data set that we are having. Now we need to compare these two and see how good the model is performing. And what is that particular step called as? That step is loss function, right? So we have already seen in the linear regression video that in any machine learning algorithm, there are three main steps. First one is the hypothesis. In our case, this whole structure will be our hypothesis. And then second step is our loss function. For loss function, the inputs will be the actual value, that is this one, and the predicted value, that is y cap. Okay, so based on these two, we'll be calculating the loss. And as it is a regression problem, which loss function can we use? We can use something like mean squared error. And finally, after these two steps, that is initializing the hypothesis and calculating the loss, then we can use something like optimizer in order to adjust the weights. So till now we have only discussed about GD, that is gradient descent. But in case of neural networks, GD doesn't work well. Okay, so the reasons we might be discussing in the next video. For this video, just understand that GD will not work good in case of ANN. Okay, what we'll be doing, we'll be, instead of GD, we'll be using something like Adam, Adagrad, RMS prop. Like that, there are several other optimizers, advanced optimizers. These we'll be using instead of this normal GD. Okay, so the reasons we'll maybe discuss in the next video. Simple reason is like GD will stop on local minimas. I hope you guys already know what are local minima and global minima and all. Basically, if we observe the graph of loss in case of linear and logistic regression, as the problem is simple, the curve of loss with respect to the parameters that we have will look something like this. But as neural networks are slightly complex, when we calculate the loss, the graph of loss might vary like this. Okay, if it is varying like this, what will happen? Like all these points, we can call it as minimas. So whatever we are seeing, all of these are minimas, but among all of these, there is only like this is the least value, right? So this we call it as global minima. So this is our global minima, whereas remaining are our local minimas. Okay, so these all points are our local minimas. So if you're using GD, we might stop at local minimas, and we might not go to, or we might not reach to this global minima. Okay, so if we are using these, then there is a possibility that we might go near to global minima. Even these doesn't ensure that we'll be going to the global minima for sure. But when compared to GD, this will be giving us the better result. Okay, so maybe in the next video we'll discuss slightly about this. Okay, so let's continue in this particular video. So we are building our network, and finally we are mentioning our loss function, that is MSE, that is mean squared error, and optimizer to be RMS prop, and metrics we are giving it to be MSE. Basically, either we can use MSE or we can go for some other score uh, calculation techniques like R to score. Okay, once we build the model and mention what is our loss function, what is our optimizer, and what are our metrics, we can simply fit our model by passing our training data. And here we are mentioning number of epochs to be 250, and If anyone of you know what are epochs, then comment down your answer in the comment section. So maybe in the next video we'll discuss about this as well. So once we fit, it will be running for 250 number of times. And initially in the first epoch, our loss is 2,57,000 something. But slowly, after running it for 250 epochs, my loss got reduced to 74, which is very less when compared to the initial loss that we have. And the 74 is very less as it is a regression problem. If it is some classification problem, then loss of 74 is very high. But as it is a regression problem, 74 is very less in this particular case. And if we check this model.summary, uh, it will be giving us what is the number of parameters for each layer. So we have already calculated this, right? We can ensure that whether we have calculated correctly or wrong using this model.summary. So this will help us in understanding the model even in a better way. And if you check model.history.history, it will contain all these loss values. So here, after each epoch, it is showing us loss and MSC, right? All those values will be stored in this model.history.history. So in loss column, we'll be having all the loss values. And similarly, we'll be having second column, that is MSC. It is not shown over here, but it will be there. And we can extract our simply loss and we can plot it. So we are taking a line plot and we are plotting the loss, and the graph is looking like this. So initially it started at 2,50,000 something. At that point it started, and slowly it reduced till 78. Okay, so this we can clearly observe from this graph. And in order to predict on some new data point, it is really simple. You can pass the input data to model.predict. So we are passing xtrain and we are getting the predicted values. And similarly, we can pass our testing data and we can get our testing predictions. Okay. So in y-test predicted, we'll be having our like testing predicted values. What we are trying to do, we are converting that into data frame. Okay, in this data frame we are having all the predicted values, and similarly in this particular data frame we are having the actual values. So in general we need to compare these two, right? That is predicted and actual values. So in order to do that, first we are concatenating both of these data frames and we are keeping it on same data frame. And basically if you see, it is actually the value is 553, but it is predicting it to be 548. Whereas here it is predicting it actual value is 578, but it is predicting it as 486. There is some slight change, but this much amount of deviation is acceptable. Okay, so in order to observe all of these values, simply we can make some plot between these two. Basically if both are same, then the plot will be giving us some straight line. If we plot these two, if we are getting some straight line, then we can understand that the value that it is predicting is really good. So let's see how the plot look like. So between actual y and predicted y, the plot is looking actually like kind of a straight line. So from this we can clearly know that the model is performing really well. Okay, basically the data that we are having is not some real world data. It is just some data that got created by making some relation between feature 1 and feature 2. That's why the neural network is able to predict well. But if we are using some real world data, our graph might not be looking like some straight line like this. Okay, and also we can use some R to score. So on training data, if you check the R to score, it is giving it to be 99. And similarly on testing data, that means our model is performing really well. That we can understand from this particular notebook. So I hope whatever that I have discussed in this particular video is really clear for everyone. If you have any doubts, please comment down in the comment section. And thank you everyone. Bye bye.